All right, welcome back. So we'll be still looking into optics today. Briefly, what we talked last time, we talked about the propagation of light and we look at the speed of light. So theoretically, it's been about 3 times 10 to the 8th meters per second, exactly this number. So this is derived from Maxwell's equation, where you get the wave function of it, and then the speed is as a result of this number. And we also talk about like the initial attempts to measure the speed of light in the previous case by several scientists. Um, we also talk about index refraction, which has to do with the speed of light in matters. So when it's in vacuum, it's this number, 299,792,458 meters per second. But when it travels in transparent medium, its speed being reduced. So the ratio between the speed of light in vacuum versus speed of light in the medium is called the index refraction for the medium. So index refraction is being a unitless quantity because it's a ratio of two speeds. And we also talk about that if the light propagates in the uniform medium, then it's not deflected. That means it goes in a straight line. So we use the ray model as the propagation of light. Okay, so if it's in one uniform medium here in the vacuum, then it travels straight forward. If it hits a median, it either get refracted or in this case get reflected. So then the direction of the propagation of light will change course. We look at the law of reflection, which simply says the incidence ray, the angle that incident ray makes with a normal direction of surface should be equal to the angle the reflected ray makes with the normal direction of the surface. So NR equal to NI. And we also look at the images formed by plane mirrors, where those images have several properties. So 3 of them listed here. So the mirror image is upright, but appears to reverse right to left. Mirror image appears to be the same distance behind the mirror that the object is in front of the mirror. And the mirror image is the same size as the object. Okay, so those are the 3 properties of images formed by prime mirrors. We also look at the refraction of the light. So when light travels from one medium and enters into a second medium, so then most of the time, the propagation of light will change direction. So in this case, in terms of the incidence angle and refracted angle, so these two angles, oftentimes they are not the same. So this is governed by Snell's law, which is also related to the index refraction of the two media. So n1 sine theta 1 equal to n2 sine theta 2, okay? And you can have the light propagate in the reverse direction of the this case here in the left versus the case in the right in this case. Because you switch the two sides of the equation, they still will apply. Okay, so the propagation of light is actually reversible in that sense. The Snell's law can be expressed also in terms of the speed of the light in the median. So sine of theta 1 divided by v1 equal to sine of theta 2 divided by v2. Okay, so because speed of light is inversely proportional to the index refraction, so then you can write them as this guy. Okay, so this is according to the definition of the index of refraction. We also look at the case when you have the light goes from a higher index of refraction median into the lower index of refraction median. So what happens is that you cannot have the instant angle increases all the way up to 90, but at some certain point, then you will lose refraction into the second media. So that means the light cannot go into the second media if your angle is greater than the critical angle. Which you can calculate it. Okay, so basically you set the refract angle equal to 90, and you get a critical angle for the instance angle. Today we'll be looking at dispersion and then also polarization of the light. So of the light, so for the dispersion, this is what is responsible for the rainbows you see in the sky. So every time I see rainbows, it remembers me this Bible verses. It says in Genesis 9:13, it says, I have set my rainbow in the clouds, and it will be the sign of the covenant between me and the earth. Okay, so but what happens is when the rainbow is displaced on the curve on the sky, scientifically, this is what happens. Okay, so as the instant ray comes in here, it actually get refracted into the media. Okay, so the different light, color of light, they actually have different wavelengths, hence different the frequencies for the different colors of the lights. So as a result, the index of refraction actually is proportional to the frequency of the light. So then if you have different colors in the light instant, then they can be separated out because they then will be refracted at different angles, okay, into the media. And then if you have a prism like this, and then so different lights will be then separate more by having a second refraction back into air. So this is then what happens. So you can actually create a rainbow by shining the white light onto a prism like this. Then you'll see rainbow at the other end, okay? And um, when the rainbow shows up, so this is what happens. So we'll skip the example for right now. We'll look at the rainbow first, and then we'll come back to the example, okay? So when rainbow shows up, it's because the sunlight hit on the water drop in air and get refracted into the water and reflected one time at the back of the water drop and then refracted again back into air the second time. Okay, so there's two, one refraction with the R and reflection with L, and then refraction again with the R. So then the white light, the sunlight, white light is a mixture of different colors will be separated. So you'll see then the violet light will be coming out about 40 degrees angles with horizontal, the red at 42 degrees with horizontal. So when you look up, the rainbows are somewhere from what you are looking into the sky at an angle between 40 and 42, okay, in that sense. In some cases, you see double rainbows. So the brighter one is called the primary rainbow. That's what we see in the previous slide. So light get refracted twice and reflected inside the raindrop one time. But for the secondary rainbow, it actually is refracted. So it works like this. So sun ray hits this guy here, refract one time, reflected twice inside the water drop, and then get refracted again. So then you can see the secondary rainbow is dimmer because it get refracted one more time. So that's an intensity lost due to that. And this secondary rainbow is typically above like 51 degrees from the horizon. Okay, so that's you look up. So that's the double rainbows that you see. Okay, so now let's go back to the example. So this one says the index of refraction for different light in liquid are different. So for one, it's 1.305. And then, so for the red light, it's 1.035. And then for the violet in the same liquid, it's 1.336. It says find the dispersion for the red and violet light when they were both they're both instant from air onto the flat surface of liquid at this angle. Okay, so light at the angle dispersion is the definition is the difference in the angle as they enters the media. Okay, so for the violet minus the red. So let's take a look. All right. So let's say this is a surface interface between the air and the liquid. So for air, index of refraction will be about, for both light will be about the same because the difference will be very small between the red and violet. So we can both use this guy, okay? For the liquid, we'll say, and for the red, n sub r is equal to 1.305, and sub v will be equal to 1.336. Okay, so normal direction as the both instance at 45 degrees. So they're coming in the same direction, right? So then index of refraction for red is smaller, so it will then bend towards the normal actually at the smaller angle. So let's say this way, or let's do red as, I think I do have red pen here, but red, okay, sorry. I initially used blue, so this is red. So this is the angle theta of r, call this theta of r. Violet, let's use just the blue for violet. Okay, so we'll bend more because violet has a larger index of refraction. Okay, so this is called the V theta sub V. So we are looking for theta V minus theta R. So then you need theta V and theta R. Okay, you actually just apply. So the instance angle is the same. Or let's call theta of I. So this is then the instance. Okay. All right. So you apply Snell's law twice for the red light. Okay, and you find your theta R. Try to focus here. Okay. All right. So then sine of theta R equals to ni sine of theta I over nr. Okay. There will be sine inverse of ni sine of theta I over nr. You plug in the numbers. So sine inverse of 1.003 sine of 45 degrees divided by 1.305. Okay, you get your angle as 32 degree-ish, 32.8093. So we keep extra digits here because these two angles actually they should be pretty close to each other because the index refraction is only like about 3% of a difference. Okay, so it's better we keep some extra digits in during the calculation. All right. So now do the same thing for the other color, the violet. Okay. So again, ni sine of theta I now equal to nv sine of theta v. So you plug in the same number, but the different n of v there, 1.336, okay, for your angle theta. So we sine inverse of 1.003 sine of 45 degrees over 1.336. And that gives you 31.95, 62 degrees. So the difference of the two angles, okay, you take those two numbers back up here, 31.9562 degrees minus 32.8093 degrees. Okay, so that gives you minus a 0.8531 degrees as the angle of dispersion. Okay. All right. Let's go back to the slide. Okay. So another interesting things that you can see in the sky besides the rainbow is so-called sun dogs. Okay, so in the morning, early morning, or in the afternoon, you'll see by the sun. Here you see two bright spots, so those are called sun dogs. So this is again due to the dispersion of light through the crystals, like ice crystals forming in the air. So then you get those, and then also this halo 22-degree halo, on the sky, that's also the ice crystals that reflected the sunlight, so then get dispersion effect. Okay, as you see. All right, so next let's take a look on the polarization of the light. So previously in volume 2, when we talk about electromagnetic wave, so we know that light as a form of electromagnetic wave, okay? So which electromagnetic wave is propagating with the vibrating of electric field, in this case, the red, and then the blue, the magnetic field, right? So this then propagate outward, okay? So sunlight that we see actually has a mixture of all this orientation of electromagnetic field and electric field and magnetic field. So it's a mixture of all this, not necessarily oriented at the same direction. So we call that unpolarized. Okay. So for the electromagnetic wave, if the electric field remains parallel to the line propagation to the direction of the propagation, the wave is then said to be linearly polarized. Okay, so a wave produced by dipole antenna is polarized. Okay, wave produced by numerous sources are usually not polarized. Okay, so for example, sunlight or the artificial light bulbs. Okay, incandescent light, etc. So those are not. You can make light polarized by using polarizers or filters. Sometimes it's also called that. Okay, so for polarized light, the vibrations lie on a single plane only. Okay, so it's only in that direction. But for unpolarized, so then the vibration of the field, electric field or magnetic field, are in all directions. So this is called unpolarized light. Okay, you can use polarizers or filters, sometimes called, so to filter out the which for filter is like the vertical openings, like slits. Okay. So then unpolarized light, when it comes out here, will just have the this portion of vertical aligned field of the light comes out. Okay, so you then get that. So then the light comes up from the filter will be polarized. So it's similar to like a wave going through like fences that like that. Okay, has openings like that. And if you have two polarizers, okay, so if like you have two of them parallel to each other, so you'll have the wave propagate through, right? But if you have two of them perpendicular to each other, then the wave will be cut off by the second polarizer. So the same thing happens to the light here. If you have two parallel polarizers or filters, then you can have a single oriented light comes through. If you have them perpendicular to each other, the two polarizer perpendicular to each other, then the light cannot go through. Okay, so you'll get a polarized light through the first filter, but then that polarized light will be cut off by the second. Okay, so in terms of intensity, as the light come out of the polarizers, okay, so the light come out of the polarizer initially is equal to I naught cosine of theta square. So in that sense, law of the molars. So in this case, so if you have the unpolarized it's been going through this first polarizer, So each of those rays, let's take rays for the light there. So on average, is having like the cosine of square average to be 1/2, right? Because you do square of it. So then through the first polarizer, you get 1/2 of initial intensity. Through the second polarizer, then you do this again, but now this I naught becomes 1/2. Okay, so then it becomes intensity comes out of the second polarizer becomes I equal to 1/2 of I naught cosine square theta. Okay, so then you can also add a third one somewhere here. The angle theta is um the direction that is parallel to the slit, which is called transmission axis. Okay, um, makes with the first or the one before this particular polarizer, all called analyzer in this case. Okay, the second one is called analyzer. The first one is called polarizer. But either way, you can also call them just polarizer instead of analyzer. Okay, so let's take a look on this example. It says two polarizing sheets have their transmission axis crossed, so no light gets through. So that means they are perpendicular to each other, right? So cosine of 90 then gets is 0. So then you'll not see the light going through. It says a third sheet is inserted between the first and two, so that its transmission axis makes the angle of theta with that of the first. Unpolarized light or intensity I naught is instant on the first sheet. Find the intensity of the light transmits through all three sheets if the angle is 45 and 30. Okay, so let's take a look on this one. We have two polarizers. Okay, so that's let's say the two polarizers are lining up like this. So this is the first one. This is its transmission exit. The second one, you want to imagine that it goes actually something like this. Transmissional axis horizontal. Okay, so then if you just have two, the angle theta between the first and the second transmission axis 90 degrees, right? So you'll get I naught here initially pass through the first one becomes 1/2 I naught, but then passing through the second one, the intensity becomes 1/2 I naught, okay, times cosine of 90 degrees squared. So that's 0. So then you get 0. Okay, so that's what happens. Now imagine you get a third polarizers being inserted in between. So something like having maybe something like that. So this is its polarizing the axis. Okay. So then through the first one is still 1/2. Okay, through the second one. Okay, so through the second one, second polarizer. I, let's call it, so this is I naught, this is I1. Okay, so then this is I2 through that. And then through the third one is called I3. Okay. Issues focusing. Okay, so after the first polarizer is I1, initially is I naught. So the second one is I2, so the third one is I3. Okay, so I1 is still equal to 1/2 of I naught. Okay, so that's the same, but I2 now becomes the 1/2 I naught. Okay, which is I1 cosine theta square. So it's asking you when theta is equal to 35 for part A. Okay, theta equal to 45 degrees. So this is then 1/2 I naught times cosine of 45 degrees squared. 45 degrees is 1/2. Okay, so 1/2 or it's square root 2 of 2 over 2, square root 2 over 2. So then square of it is 1/2. So this is 1/4 of I naught. I3, which then will be equal to I2 cosine of the angle between this one and this one. So if this guy and this guy has an angle of theta, so then between these two should be 90 minus theta. Okay, so 90 minus 45 degrees. So in that sense, it will be still 45. Okay, but then I2 it's actually 1/4 of I naught, and then square root 2 of square. So that gives you 1/8 I naught. Okay, so when the light goes through the third one now, it's not 0. You have actually just 1/8 of the original intensity. For B, you do the same thing. So theta equal to 30. So then you just change this guy into 30. So this one will be still the same. Okay, I1 is still 1/2 of I naught. I2 is equal to 1/2 of I naught cosine square of 30. Okay, cosine of 30 is 1/2, or actually this square root of 3/2. Okay, so then square it becomes 3/4, so you'll get 3/8. Actually, I naught. I3 then equals to I2, which is 3/8 of I naught cosine of now 90 minus 30, 60, and squared. So cosine of 60 is 1/2, so then you get 1/4. Okay, so you get 3/4 times 8, 32 I naught. So this is then what you get. Okay, after it comes out of the second or the third polarizer. All right, let's go back to the slide. So in addition to using polarizers, you can actually get polarized light by having looking at the reflected ray. Okay, so this unpolarized instant ray, if it's on the surface, when it gets refracted partially and reflected, so you have to tune the angle of instance. So then these two makes an angle of 90 degrees. So then this will be polarized reflect rays. Okay, so according to the relationship, this angle should be equal to this guy. And if this makes a 90 degree, okay, if this angle is 90 degree, so then this angle will be 90 minus this guy. Okay, so then yeah, the refract angle is 90 minus the instance angle. So take that into the equations, you'll get theta of the 90 minus theta p will be actually cosine of theta p. Okay, so then tangent of theta p is n2/n1. So then you can find the angle. So this is called a polarizing angle or Brewster's angle. Okay, and there's a technique called Brewster's microscope, which is then actually setting this up, and then you'll be looking at the polarized reflect ray. Okay, for the to the microscope to look at the interfacial structure in that sense. The applications of polarizing light, okay, is mainly what we have seen in sunglasses, as well as in some cameras lenses. So let's take a look on here. So if you have polarized sunglasses, so then it will reduce the refraction from the background. So normally in the horizontal direction for the refraction. So if you filter that out, then you actually see things more clearly than this guy. Okay. Also, like if you are attending a sporting event or other event, and if there's a lot of refraction from the background, then wearing polarized sunglasses will help you actually reduce the background, okay, refraction, so then you can see things more clearly. And for lenses as well, okay, so the backgrounds are pretty much from the refraction, horizontal refraction. So if you use the polarized lenses, you'll be able to capture more of the details of the picture, okay. And then of course also seeing through glasses as well, because the glasses will have reflection to the observer in that sense. Okay. The last method is called polarization by scattering. So when the unpolarized hits on the surface, okay, so it gets scattered all over the places. So in the direction that is perpendicular to the instance ray, so then you get actually polarized light beam, okay? So in that sense, so then you can also obtain polarized light by just looking at the 90-degree angle with respect to the instant beam, okay? All right, we'll stop here for today. We'll come back for other topics next time. So see you guys next time. Bye.